morning, friends and dear students. It gives me immense pleasure to be here again for this course, Engineering Thermodynamics. As of now, I have completed some basic concept about pure substances, some properties of the pure substances, PV and TV diagram of a liquid, vapor and superheated conditions. Today my topic is Zeroth Law of Thermodynamics. This Zeroth Law of Thermodynamics, this was postulated after the first law, second law and third law of thermodynamics. However, this was named as a Zeroth Law of Thermodynamics by Fowler. Why it is Zeroth? Because the first law, second law and third law, all the three laws were developed, and then this law was developed. It was not named as the Zeroth. There was lot of debate between so many scientists that what the name we have to give for this law. And at the last, the Fowler, he decided in a debate, and all have come to the conclusion that the name of this law should be given as the Zeroth Law, because being it was found at the last, but this should exist before all this law. So all the three names, first, second and third law were given. So this name was postulated as a Zeroth Law of Thermodynamics. This is very, very important. This gives about the equilibrium state of any substances. And it is very interesting, and we will come to know about Zeroth Law in this lecture. In today's lecture, I am going to discuss about basic thermodynamic properties, few, just like pressure and temperature. That is temperature and the pressure I am going to revisit. Then I will go for the Zeroth Law of Thermodynamics and what it states. Then I will go for thermal equilibrium, because Zeroth Law of Thermodynamics gives and tells about equilibrium of substances. Then application of Zeroth Law of Thermodynamics, I will give some example in this application part of the Zeroth Law of Thermodynamics. So let's go for our next slide, that is the basic thermodynamic properties. So we know that for any pure substances, we require minimum two properties by which we can give the state of any substance. So if we see that I have shown the previously also that if you want to give any state, so suppose it is a specific volume and this is the pressure, and if you want to give anywhere, one state is here 1, so this is your pressure, this much is your pressure from here to here, and from here to here this is the specific volume. I am writing V1 and here I am writing P1, so this will be P1 and V1. So this is the state 1. If you want another state, so another state is here 2. So this property, if I put here vertical like this and here the horizontal line like this is the P2 and here is the V2. So this state is P2 comma V2. So like this, we need minimum 2 states to describe. So here I am only discussing about 2 basic properties of thermodynamics, that is the pressure and the temperature. So we can see here that thermodynamics can be defined as the study of energy, energy transformation and its relation to matter. So if you see here, if I have this palm and if I rub like this, my palm is getting heated. So how this heat I am getting? So the work energy which I am putting by my hand and by the friction of this heat, my work is converted to the heat. So here is work is also energy, heat is also energy. So thermodynamics is the study of energy transformation and its relations with the matter. Here I have my skin. Sometimes we may have water, refrigerant, or any blood, air, any material or any substances. We can take it, and this thermodynamics deals with every branch of engineering. It is not only mechanical or aeronautical. It is for all electronics, computer science, even economics also. Thermodynamics is applicable. So this is the uh, thermodynamics can be defined as the study of energy transformation and its relation to the matter. The analysis of thermodynamic system is achieved through the application of the governing conservation equations. So here we do the analysis of any thermodynamic system by some governing equations. Namely, we have mainly three governing equations, that is called conservation of mass, conservation of energy. This conservation of energy in thermodynamics, we call it as a first law of thermodynamics, and the second law of thermodynamics, that is the how much efficiency. The second law of thermodynamics gives about the efficiency of the system. So, and its property relationship. So there are mainly three governing equations, that is conservation of mass, conservation of energy, and conservation of momentum. So these all three or governing equations are used in thermodynamics. Energy, what is energy? Energy can be viewed as the ability to cause changes. Now, what is the system? It is very important, and I have already discussed the system. So if you see here that this is the some space, and here inside some gas is filled. So if we study about this, so this is the system. The properties of this thing is what? That in the system we consider two types of system. One is the closed system, another is the open system. In closed system, mass will remain constant. Mass will be constant. Only energy may go out or it may come in. So energy transfer will take place, but mass will remain same. So here if you see, a system is defined as the quantity of matter or a region in space chosen for the study. So if you can see in this diagram, I have shown this dotted line, and this dotted line represents that this is our system. And in this system, whatever material or matter you are putting inside this is called the system. So the mass or region outside the system is called the surrounding. So this is the system, and here is the surrounding. So if you take the example of a teacup, so just I am showing here. This is a cup. Inside we have the hot coffee or tea, whatever you can see. And here if you see, some gases will come out. Here is your room. This is the room where we are. So if you see that the hotness and the coldness of this cup will not be felt outside of the any other places. Only some, I will just put some distance outside of this cup. This is your system, where the difference of, and this is called the surrounding. Your room is surrounding, and this is called the boundary. This line which I have drawn here, dotted line, this is called the boundary. Okay. So this is the the mass of a region outside the system is called the surrounding. So this is the system. I am writing, is hatching like this. This is the system, and outside this system here, this is the surrounding, and this is the boundary, and the summation of system and the surrounding is called the universe. This is the universe. Total of this, including system and the surrounding, is called the universe. So that is the difference between, and we should understand the systems and the surrounding, because for our analysis we should take care of the system and which type of systems we are using and how and where we are using, we have to take care of. So here I have shown one diagram. In this we can see that there is a system, and I have just now told that effect of this thing is felt inside this. This dotted line is a system, and outside this dotted line is surrounding, and the boundary, this, all these boundaries, they are the system boundaries, and the summation of the system and the surrounding is called the universe. So this we can see here, that in this way we can define the system, and understanding the system is very, very important, because if you want to do the analysis, we do a certain region. In that only our thermodynamics laws are applied. Now I will go for the next, a very important property. It is called the pressure. So what is the pressure? Pressure is the force exerted by a fluid per unit area. So if you see here that anywhere, if this is the your things, and here there will be number of molecules. These molecules will move randomly here and there, and they will hit this wall. So they will hit like this, like this, like this. So there will be a force per unit area. So they all generate, and this is your area, assume this is the area, and a force is generated. This is the force. So force per unit area. So the force exerted by a fluid per unit area. So that is the meaning of the pressure, and pressure is equal to force divided by area. The unit of the force is Newton, area is meter square. This Newton meter square is called the Pascal. The unit of this thing is Pascal. So this we have to see that this is the Pascal, a name of the scientist. By his name this thing has come. So per square area force in fluids, gases and the liquid we speak of as a pressure. In solid, this is stress. So if you take a solid rod or any material, metal particle, there it is called the stress, because as you pull or the push, the force per unit area is a stress. So stresses are developed in the solid, and the pressure is developed in the fluids. For a fluid at rest, the pressure at a given point is the same in all directions. So if the fluid is in the rest, so pressure in the point is same in all the direction. So this you can see here, that how a depiction of this pressure forces. So if you see here that pressure of a fluid at rest increases with the depth. So if you see here, this is the height, and if you see here, as you go up and up, at the in this edge, at the top of this, you don't have any pressure, but at the bottom you have the more pressure, because if you see here, the height of this fluid, as you are increasing from here to here, here to here, here to here, here to here, and here to here, more pressure is acting on this. So if you see here, the P is equal to weight of the liquid divided by area. So weight of the liquid, how you can find out? M and G, mass into gravitational force divided by area. But we know about the mass. Mass is rho AH, means density into volume here. A, area, H is height. So this volume of the fluid, density into volume into G by A, and this A and this A is cancelled. So you will get rho Hg. So this pressure P is equal to rho Hg for a fluid which is stationary, and it is directly proportional. P is directly proportional to the height of the fluid. So this is a simple explanation of the pressure on the system. So the actual pressure at a given position is called the absolute pressure, and it is measured relative to absolute vacuum. Very much we have to understand that there are three types of pressure. One is absolute pressure, one is the atmospheric pressure, and another is a total pressure. So we have to understand these all types of pressure. So gauge pressure is absolute pressure minus atmospheric pressure. So there is atmospheric will press. So if we measure above the atmospheric pressure, then it is called the absolute pressure will convert to the gauge pressure. So gauge pressure is equal to absolute pressure minus atmospheric pressure on the system. So here this you can see that the gauge pressure P gauge is equal to P absolute minus P atmosphere, where this P is greater than P atmosphere. So when this total pressure P is greater than atmospheric, we have to use this. Then P vacuum, here this P is less than the atmospheric pressure. So this P vacuum is equal to P atmospheric minus P absolute. Here by this diagram, we can depict that what are the systems which are working and how this pressure at different levels are described. So here this we can see pressure and the specific volume. So here if you see, this is the line here. Here is P vacuum. Then here we have the P gauge, P atmospheric. So just you see P absolute. This is the atmospheric pressure. From here to here, this is the atmospheric pressure. And if above atmospheric pressure, it is a P gauge. So here, how much is the total pressure? From here to here is a P absolute. This P absolute is equal to P atmospheric plus P gauge. GAU, P gauge. Or P gauge is equal to P absolute minus P atmospheric for this condition. Okay, and if we want to compare P vacuum, so from this line, it is from the P atmospheric line, if it is less than that, so P vacuum, this one is equal to P atmospheric, this minus this absolute. So this temperature, how much? This, it is called the P atmosphere. From here to here, P atmosphere, and from here to here, how much? It is a P absolute. So P vacuum is equal to P atmosphere minus P absolute. P absolute. So this is very, very important for each and every student, because the pressure, which pressure is given? It is a gauge pressure, atmospheric pressure, or atmospheric and gauge pressure, or the this absolute pressure or vacuum pressure. There are four types of pressure which is existing, and for the absolute condition here, vacuum is 0. There is no vacuum at all. So now I have to see one example, and we will try to do this with the help of same principle which we have discussed just now. The piston of a cylinder piston device has a mass of 60 kg and a cross-sectional area of 0.04 meter square as shown in the figure below. The depth of the liquid in the cylinder is 1.8 meter and has a density of 1558 kg per meter cube. The local atmospheric pressure P atmosphere is given 0.97 bar, and the gravitational acceleration G is given 9.8 meter per second. Determine the pressure at the bottom of the cylinder. So we have to find out pressure at the bottom of the cylinder. How much pressure is given here? This we have to find out. So this I have shown here this diagram. P atmosphere is given 0.97 bar. Mass of the piston is given here 60 kg. So we can multiply it by 9.8. So you will get the weight. And the density of this thing is given rho is 1558 kg per meter cube. The local atmospheric pressure is 0.97 bar. This given. And the gravitational is 9.8. G is 9.8. And this height from bottom to this point is given 1.8 meter. So we have to find out how much pressure is existing. So that is very important. So here the pressure at the bottom of the cylinder can be found from the summation of the forces due to atmospheric pressure, piston weight, and the weight of the liquid in the cylinder. So there are three things. One is the atmospheric pressure, one is the weight, this is the atmospheric pressure, this is the weight, and piston weight, this is the piston weight, atmospheric pressure, and the liquid weight from here to here. How much is the liquid weight? We have to sum it up and we will get the answer. So here we can see that the solution of this problem, given mass is equal to 60 kg, area is 0.04 meter square, height of the liquid is equal to 1.8 meter, density of the liquid is 1558 kg per meter cube, atmospheric pressure is 0.97 bar, and G is equal to 9.8 meter per second. So this we have to use this, that total weight, the bottom of this, if you see here, this is the bottom. So how much it is there? So here is the atmospheric. So here we have the atmospheric pressure. This is here the piston pressure, piston weight. And here is the, from here to here is height, H. So here you will get rho GH. So the total weight at the bottom will be P atmosphere into A, area of this. This is the area. This is the area. Plus weight of the liquid. Here is the liquid. This is the liquid. This is the liquid. Plus weight of the piston. This is the piston here. Okay. So this we can see that. So now if we, this W by A, here also A, and here also A, and here also A. So what we will get here? P pressure at the bottom, because force per unit area. So we got the pressure. And here this area and this area is cancelled. P atmospheric. Here this is the mg by A, and this is rho GHA. A is cancelled, so rho GH. So this pressure at the bottom is equal to summation of the pressure at the atmospheric pressure plus mg by A, that is the piston weight, and this is the fluid weight. So all these parameters if we put here, we know that atmospheric is given 0.97 bar, just you can see here, this is given. Then we have the 60 kg, this you can see mass into acceleration G, 60 into 9.8, area is equal to 0.04 meter square, plus rho is given 1558 kg per meter cube, G is 9.8 meter per second, and height is 1.8 meter. So we can see here that this is the Newton meter per meter square, 1 kg per meter square, 1 bar. This is, you will get 1.3918 bar. So this is the answer. You at the bottom here, the total pressure here you will get as a 1.3918 bar. However, if you see the atmospheric pressure is already given 0.97. So the liquid and all, they are giving some sufficient amount of pressure or increase. Now I will discuss the next very important property in our thermodynamics. Three properties are very, very important. One is the pressure, another is the temperature, and third one is the specific value. They are intrinsic property. These properties are not depend on the mass. How much mass is there? They will remain constant how much you reduce the mass. So that is the specialty of the intrinsic property. We need minimum two properties to identify any state. So here only I am discussing about the pressure and the temperature. Pressure I have already explained. Now I am going to discuss about the temperature, because my topic of the day is Zeroth Law of Thermodynamics, and this law describes about the temperature. So that is very much essential. So what is the temperature? Temperature is a pointer for the direction of energy transfer as heat. We know that always the heat transfer will take place from high temperature to low temperature. So temperature is like a direction. It is like a pointer which describes about the system, and temperature is a pointer. It is like a direction indicator of the direction of energy transfer as a heat. We can see here that, you see, if this temperature of A body is higher than the temperature of B, so this Q, heat will transfer from A to B. But if the temperature of this B is higher than the temperature of A, then heat will transfer from B to A. This you can see. If the TA, the temperature of this is less than the temperature of the B, the heat will transfer in this direction. And if temperature of A is higher than the temperature B, then it will move from here to here. That we have to understand. When the temperature of two bodies are the same, thermal equilibrium is reached. And you see, if this is the 100 and this is the 60, it will try to move. So if it is the 80 and this will also 80, so if both are 80 from this and this, the transfer will not take place. Heat transfer will not take place. So that is the beauty of this temperature. So temperature also makes sure that the systems are in equilibrium. So that we will be discussing in this Zeroth Law of Thermodynamics. Very important. Just now I also told, this is a very latest comparing to the first law, second law and the third law. The Zeroth Law of Thermodynamics is the last. So it was full debate. We should give the fourth law of thermodynamics or we should give some other name. So many scientists were gathered and they were doing the debate. And lastly, the Fowler, he has given a very good suggestion that since the temperature, it defines the equilibrium and the temperature of a body, and our first law, second law, third law, they also define the temperatures, the application of the temperature and the heat transfer. So before that, it should be placed. So already first, second, third law were there. So it was named as the Zeroth Law of Thermodynamics. So that is the story for the development of this Zeroth Law of Thermodynamics. So here I will, one of the four laws of thermodynamics is the Zeroth Law of Thermodynamics. There was a debate whether it should be fourth law or another name, as first law, second law and third law were already postulated by Joule and other Kelvin and other people. So we should make a fourth law or other name, and after a lot of debate it was discussed. So R.H. Fowler eventually came up with a name that would put an end to this argument. So there was a discussion and all, and Mr. R.H. Fowler, a renowned thermodynamic scientist, has put up the idea that we should give the name of Zeroth Law, and this argument was ended after his suggestion. The concept of temperature as an indication of thermal equilibrium is framed by the Zeroth Law of Thermodynamics. So the concept of the temperature. So what this thermodynamic, this fourth law, this Zeroth Law is doing? It gives the concept of temperature as an indication of thermal equilibrium is framed by the Zeroth Law of Thermodynamics. So this Zeroth Law of Thermodynamics is actually, it gives about concept of the temperature and thermal equilibrium is framed by this law. So before we go for further discussion of the Zeroth Law of Thermodynamics, how it was evolved, we should also discuss there are some types of wall or some types of arrangement which try to make the system isolated or give a nice conductive environment. So first wall is called the adiabatic wall, where no heat transfer takes place. So what is the meaning of adiabatic? If this is a chamber and there is a wall, this is the wall, there is some fluid X, and here is some fluid, another fluid Y. So it may, here is some parameters, any thermodynamic parameter, pressure, temperature, specific anything, it will not allow to transfer from here to here or here to here. It will not give, it will make isolate. The system will be isolated. This wall will not allow to transfer energy from X to Y or Y to X. This is called the adiabatic wall. This is called adiabatic wall. So adiabatic wall where no heat transfer take place. So whatever temperature here, may T1 or the T2. So T1 will not go to T2 and T2 will not allow to go to T1. So there will not be any heat transfer between X to Y or Y to X. And this, if you have such type of wall where there is no heat transfer, then it is called the adiabatic wall. So this wall here is a adiabatic wall. Okay, so this we have to understand, because without understanding these two walls, somewhat difficult to understand the Zeroth Law of Thermodynamics. Next wall is diathermic wall, which allows heat transfer to take place smoothly. So if you see here, another wall, it is called the diathermic wall, and if this is the X and this is the Y, this will give heat will be transferred from high temperature to low temperature T1 to T2, where T1 is greater than T2. Very smooth flow of heat will be there from high temperature to low temperature with any wall. That is called the diathermic wall. So we are going to discuss about now Zeroth Law of Thermodynamics. So we should take very cautious approach for this thing, and you can see that what is the statement of the Zeroth Law of Thermodynamics. This law states that if two bodies are in thermal equilibrium with a third body, they are also in the thermal equilibrium with each other. The Zeroth law makes a thermometer possible. Very, very important that if there are three bodies and if the two bodies are separately thermal equilibrium with the third body, then they are also in the thermal equilibrium with each other, and this gives the thermometer. How we can measure the temperature, we will be discussing in due course of time. In accordance with the Zeroth law, any system that possesses an equation of state that relates temperature T to other accurately measurable properties can be used as a thermometer, e.g., an ideal gas obeys the equation of state. So, in accordance with the zeroth law, any system that possesses an equation of state that relates temperature T to other accurately measurable properties can be used as a thermometer. So, we know that PV is equal to mRT. So, if you know this T or temperature, we can measure by the P or by the V. Anything we can vary, and this will be directly related for this. And this principle, the state equation, was used to measure the temperature of any given gas, because R is constant and M is constant. So we can see here that T is equal to PV by mR. So this is state equation. This is state equation is used for measuring the temperature by varying the pressure or the volume of any substance. So experimentally obtained temperature scales, the Celsius and the Fahrenheit scales, are based on the melting and boiling point of water. So these two basic scales, that is the Celsius and the Fahrenheit, they are made by boiling point of water. They are also called the 2-point scales. So here one is the freezing point, another is the melting point, like this. The melting and the boiling point of the water, and they are differentiated, and they are called the Celsius and the Fahrenheit scale of the system. Then conventional thermometry depend on material properties, like mercury expands with temperature in a repeatable and predictable way. So we use some materials like mercury, and if we give the heat, this will expand in the directly proportional to the temperature, and it will repeat. How many times you do, it will reach in the certain amount, the height it will achieve. So like this, a conventional thermometry was used, and you can see the medical thermometer which we are putting in our mouth to measure the temperature. The doctor and all, they measure in Fahrenheit. So this type of thermometers are used. With the help of inside we put the mercury, and as the body you put, so here your mouth or your body is one system, the glass tube is another system, and the mercury is another system. So like this we have the A, B and C. So if A and B are equilibrium, the C will also be in equilibrium. So the distance of your mercury will show that how much amount of temperature you have. So like this, it was very nicely, and zeroth law gives about this type of measurement. Thermodynamic temperature scales depend upon the material. The Kelvin and the Rankine scales are determined using a constant volume gas thermometer. So in this Kelvin and this Rankine scales, they are absolute scale. They are not from freezing point or the boiling point of the water. They have used the constant volume gas thermometer. So in this, they have used this volume of this thing, and this volume will give this volume is constant. So this, as per that, they have measured, and they have given the degree Kelvin or the Rankine scale. So here I am going to discuss about zeroth law of thermodynamics, and I want to just discuss about how this law was evolved and how this thing can be explained. This you can see here. Before that I have discussed about the adiabatic wall and the diathermic wall, and this I have taken from the reference 1, zeroth law of thermodynamics. So here this you can see, if two systems here, system A and the system B, separated by a wall that does not allow any exchange of energy between them. So we have a wall, very thick black color wall, and this does not allow that A to B or B to A. There is no transfer of energy between two systems. Okay, so this is the system A and the system B. The third system C is separated from the system A and B by a conducting or diathermic wall. So now the third system here is the C, and this third system here we have made a diathermic wall. We know that diathermic wall is the wall which is very smoothly, it will transfer the heat from one to another. So if we make here, then what will be there? So if two systems A and B separated by a wall and that does not allow any exchange of energy between them, such a wall is known as the insulating wall or an adiabatic wall. So this is also called the insulating wall. The third system C is separated from the system A and B by conducting or diathermic wall. So this is the diathermic wall or conducting wall. Simple word is called the conducting wall. This wall is made in such a way that it will be very smooth transfer of energy. It will be there till the time its strength is permitting. It will allow the system energy to be transferred. Energy can be exchanged between system A to C. So both A and C are in thermal equilibrium. So from A to C, energy will be transferring. So after some time, A and C will be in thermal equilibrium. Similarly, energy can be exchanged between system B and C. So this energy can go from here to here. So from here to here, it will also, both B and C are also in the thermal equilibrium. But after some time, just like A and C are the equilibrium, now B and C are also equilibrium, both systems. So now what will happen? The both systems, they are not A and B, they are not connected, they are separated by adiabatic wall. This adiabatic wall is not allowing to transfer anything from here to here, here to here. Not possible, not possible. But because this system is here, so after some time, A system and C are in equilibrium, B and C are system equilibrium. But after some time, A and B and A both will be also in equilibrium. So that is called the zeroth law of thermodynamics. Both system A and B are in thermal equilibrium with the third system C separately. That is the essence of this zeroth law of thermodynamics. So when the adiabatic wall between A and B is removed, no transfer of energy takes place between them. So after the equilibrium has reached, if you remove this, nothing will happen. All will have the same state of thermal condition. So that is the fully equilibrium condition is met. This shows that system A and B are also in thermal equilibrium with each other. So now, if you see here that the observation leads to an important law known as the zeroth law of thermodynamics, which is stated as follows. Two systems A and B, which are separately in thermal equilibrium with a third system C, are also in the thermal equilibrium with each other. So this is the zeroth law of thermodynamics, this one. According to the zeroth law of thermodynamics, if system A is in thermal equilibrium with a system C, then the temperature of the system A is equal to temperature of the system C. Similarly, if system B is in thermal equilibrium with system C, as shown in the previous diagram, then the temperature of the system B is also equal to the temperature of the C. So just you can see A is equal to C, B is equal to C. So by mathematics, A is equal to B. So that is the temperature of A is equal to temperature of the B system. Thus, the temperature of a system or a body can be defined as follows. So what is the definition of the temperature? The temperature of a system is a physical quantity, equality of which is the only condition for the thermal equilibrium of two systems or body in contact. So what is the temperature of a system is a physical quantity and equality of which. So if the temperature is equal, is only the thermal equilibrium will be happen in between two systems. Or this we can see that a system or a body temperature is a physical quantity that indicates whether or not the system is in thermal equilibrium with another system with which it is touched. So if a body is in hot and you touch a cold body, the hot body will transfer to the cold body. So a system or a body temperature is a physical quantity that indicates whether or not the system is in thermal equilibrium with another system with which it is touched. So now I will discuss a next important topic, that is thermal equilibrium. And this thermal equilibrium just now I have explained in my Zeroth law, if A, B and C, and how these things are happening. The Zeroth law of thermodynamics says that no heat flow will occur if the system are in thermal equilibrium. So Zeroth law is telling that if two systems are having the same temperature, there will not be transfer of any thermal energy or any heat will not be transferred. When two or more bodies of different temperatures come into touch, they eventually reach a similar temperature and are said to be thermal equilibrium. So when we take the two bodies, body A and body B, when two or more bodies of a different temperature come into touch, they eventually reach, and if you put here one diathermic wall, this is a diathermic wall, means it is a full conduction wall, they eventually reach each other similar temperature. So if it is 100 and it is 80, after some times both body, this body and this body, this is B and this is A, both will be 90 degrees centigrade and this will be 90 degrees centigrade. So that is called the equilibrium. Reach a similar temperature and are said to be in thermal equilibrium. So they are in thermal equilibrium. Systems are considered to be in thermal equilibrium if there is no heat transfer. So in this case, if both are having the 90 degree, there will not be heat transfer. In this case, heat transfer Q will take place from A to B, A to B, A to B, till the time both are not having same temperature. In next case, if this is reached 90 and this is the 90, there will not be Q, will not be in this case. So that is the systems are considered to be in thermal equilibrium if there is no heat transfer is taking place. Example, I am giving a very popular example. In our home, we have some refrigerator. We all have food in refrigerator. So no heat transfer between food and the refrigerator air. So your refrigerator is making the temperature of your food item, your fruit and all the same as the chamber. So there will not be heat transfer between your apple to the surrounding and it will remain in the same condition. Next, Zeroth Law of Thermodynamics, examples and application. This is very important aspect of Zeroth Law, and it is very much useful for measuring the temperature and thermometry and all. So this law the zeroth law is crucial for mathematical formulation of thermodynamics or expressing the mathematical definition of temperature. So just now I have told you that if A is equal to C, just now the previous slide, if A is equal to C and B is equal to C, so A is equal to B. So this is your zeroth law. So this is a mathematical equation. So this is the equation 1, equation 2, and this is the equation number 3. So like this mathematical expression of your thermodynamic properties we can do by help of zeroth law of thermodynamics. The most common use of this concept is to compare the temperature of different things. So we can compare that if 3 or more items are there, you can see that which one is in high temperature, and from high temperature to low temperature the heat will transfer. If you want to accurately measure the temperature, we will need a reference body and a characteristics of the body that changes with the temperature. So we need a reference body, like for the centigrade we need the water from ice to the vapor. So we need one media, or characteristics of the body means the water will go like this, and at this temperature it will be freezing. The change in that characteristics could be interpreted as a temperature change. So like in the medical thermometer, we are putting some mercury. That mercury will expand in the same ratio as the temperature is, and we can calibrate it and we can give that it is 0, 1, 2, 3, 4, 5, like this we can make it. So thermometers are the most prevalent application of the zeroth law of thermodynamics. So if we talk about the application part, so thermometers are the most useful application of the zeroth law of thermodynamics. Depending on the thermometric characteristics, several types of thermometers can be utilized. The following is the list of thermometer. First one is the constant pressure gas thermometer. If it is a, we know, I have shown you that PV is equal to T by MR. No, sorry. P is equal to PV by MR. So here, in this case, volume is constant. So pressure is, so in this, PV, so here pressure is constant. So volume of this thing will be vary, and this volume will be directly proportional to the T. So that is the first case. Second thing is we can vary the, we can make the pressure volume constant and pressure will vary. Then electrical resistance thermometer, in this we, as per the temperature, the resistance, this is R will change as per the temperature of, it is directly proportional to the T. Mercury in glass thermometer, the length of the mercury will change, and thermocouple, the electromagnetic force will change, and here we will measure this, we will measure the length, we will measure the, we will pressure, and we will measure the volume. Accordingly, in the same ratio, your temperature will be calibrated and it will be displayed on the particular scale. So now I will give some example, some sample problem of zeroth law of thermodynamics. Very, very interesting. I think you all will enjoy these examples. I am just, first example I am giving you, that body A comes into contact with body B, which then comes into contact with the body C. A has a higher temperature than B, which is higher than C. According to zeroth law of thermodynamics, what is the proper flow direction? So this you can see here, that the heat will travel from point A to point B to point C, eventually reaching the same temperature. So here, just I am showing you here one example: A, B, C. This is the 100, this is the 80, and this is the 60. So this is the A, this is the B, and this is the C. So how the heat transfer will take? First from this 100 to here, and from 80 to 60, and it will continue from 100. This 60 will reach to the 80, will reach to the 70. This will be 70. Okay, this 100. So sometimes all the temperature. Okay, so this 100, and sometimes all temperature will be the same temperature. So till the time temperatures are not same, A to B, B to C, and this flow will continue. So okay, so 186. So all will be at 80 degree centigrade. Okay, so like this till the time the transfer will take place. Now the problem 2, give any one application of zeroth law. So I will just boiling of water in 2 cups with thermometer. So how I can tell that how much is the temperature? So there is a 1 cup here, A, another cup is B here. So how boiling of water? So here I have given some heat. Okay, so we know that, and if I put a thermometer here, okay, so in this case I am heating. So as and when it is reached to the maximum 99.6 degree, then temperature of this thing will not increase. So just we will wait up to 99, and as and when it reaches to this, temperature will not increase. Then we will remove this thermometer and put in this and give the heat here. This heat will increase, and this also increase till the time it is 99.6. So by this is A, B, and this thermometer is C. So A and C, B and C, and this C is making sure that both are in the A and B are in the same equilibrium condition. So that is the application and example of this zeroth law of thermodynamics. Now I will go for the problem 3. Which scale was added by the zeroth law of thermodynamics? So the zeroth law of thermodynamics refers to thermal equilibrium or entities that do not exchange heat. Heat flow is caused by temperature difference. As a result, this law aided in the measurement and identification of temperature as a universal attribute of matter. So this zeroth law of thermodynamics will indicate the temperature and how to measure the temperature and how to identify the temperature, and that has become the universal attributes of any matter. So this scale was added by this law. Now constant volume gas thermometer, as per the syllabus we have. So a constant volume gas thermometer usually consists of a bulb filled with a fixed amount of dilute gas which is attached to a mercury manometer. The manometer is used to measure variation in pressure. This thermometer works on the principle of law of Gay-Lussac. The law states that when the temperature of an ideal gas increases, there is a corresponding increase in pressure. So in this volume V remains the constant, and as it is in a manometer, so this pressure is directly proportional to the temperature. So law states that when the temperature of an ideal gas increases, there is a corresponding increase in pressure. So P and T are increasing. This is how constant volume gas thermometer traces the increase in temperature with the change in pressure while the volume remain constant. These types of thermometers are used in calibration of various other thermometers. So these are used for this purpose. It is called constant volume gas thermometer. So here volume of a gas at T degree centigrade is 20 liter. When temperature of gas increases by 50 degree centigrade at constant pressure, then volume of the gas increases by 25%. Then calculate value of it. So we have to find out it is in fact then pressure, then it is not then, it is then. Okay, so we have to see that here given V1 is equal to 20 liters, T1 is equal to T degree centigrade. So we know that V2 is equal to 25 by 100 into 20 plus V1, because it is increasing by 25%. So 25 by 100 into 20 liter. So 25 by 100 into 20 plus V1. Here we have the 5 liters. We have the total 20 liters. So 20 liters into 25 by 100 into 20, it is 5 liter. So the V2 will be 5 plus 20, it is V1 into plus V1. So here 5, it is 25 liter. So V2 is equal to 25 liter. Now T2 is equal to T plus 50. So initially it is T and now it is increased to 50. So volume of the gas, then second state, that is a T2 is equal to T plus 50. We know that V is directly proportional to the temperature. So V1 by T1 is equal to V2 by T2. So we know the T2, we know the V2, we know the V1. We have to find out the T1. So T1 is equal to T. So 20 by T is equal to 25 by T plus 50. So we can do it here that 20 into T plus 50 is equal to 25T. So 20T plus 1000 is equal to 25T. So 25T minus 20T is equal to 1000. So 5T is equal to 1000. So T is equal to 1000 by, so T is equal to 200 degrees centigrade. Okay, so like this we can find out the T is equal to 200 degrees centigrade. So this is the answer of this problem. In the next class, I will be discussing about concept of temperature, principle of thermometry, factors that determining use of thermometer, fixed point, thermal expansion, types and calibration of thermometer. This I will be discussing in my next class. These are my references from PK Notebook, Sengel, and also NPTEL lecture from IIT Kanpur. Any questions you are welcome to ask. You can ask any questions to my mail yd.dwivedi@gmail.com.
Like, share and subscribe. Hit the bell icon for more updates.